Okay, everyone, today we're going to be talking about molecular geometry. So you've seen this document before, and I've included all this information up here for you to look through. But in this lecture video, we're going to actually work our way through this chart and try and make sense of what is going on here. So I'm basically going to recreate this chart and kind of walk through it. The first example occurs when we have essentially 0 lone pairs and 2 bonds. So 2 bonds. And what these two things are talking about, number of lone pairs and number of bonds, is in relation to a central atom. So in the chart, what that means is like atoms bonded to central atom. So that's literally like how many bonds do you have? How many lone pairs are there on the central atom? And then the total number of electron domains. So an example of this would be CO2, which looks like this, or has a Lewis structure that looks like this. So you'll see that on the central atom, right, this is always talking about in relation to a central atom, that there are 2 bonding regions. So I guess that really shouldn't be number of bonds. It should be bonding regions. Okay. And there are 0 lone pairs. Now the hybridization for that carbon is sp. And, oh gosh, I did not leave enough room here for this. But anyway, this would be linear. So the shape is literally a straight line, and the angle is 180 degrees. So it's just like exactly like a straight line from geometry. Now the next example would occur when there are 0 lone pairs, 3 bonding regions. This is an example of an sp2 hybridized atom. And an example of that would be BCl3. Okay? This would be an example of trigonal planar. So trigonal planar means that each of the chlorines and the bromine are all in the same plane. So if I turn this molecule on its side, what it would look like is a flat disk. So here's like a boron and a chlorine, right? So it would look like a flat disk. That's what I mean by planar. Trigonal in the sense that it's looks kind of like a triangle. Now, if you split a circle into 3 pieces, the bond angle here between chlorine, bromine, chlorine is 120 degrees. So the boron, the chlorine, boron, chlorine bond angle is 120 degrees. It's the same thing as if you have a circle and you split it into 3 pieces. Each one of these has got to be 120 degrees because the total angle of a circle on the interior is 360. Okay, so those are pretty straightforward so far. That's the first 2. So we've got linear, trigonal planar, right? We've got 180, 120. Now, the next thing we can have is if we have 1 lone pair and 2 bonding regions. This is still an example of an sp2 hybridized atom, and this could be something like SO2, which looks something like this. So this would be an example of something that is, I believe, they call it angular. I think you can get away with calling this bent also, but we'll just call it angular because why not? So angular, right? No bond angle that's so important here. That's fine. Okay. So now let's get into the ones that we see most often. Gosh, these are getting really bunched up, huh? I'm just going to erase these actually. This makes more sense. Okay. So if we have 0 lone pairs and 4 bonding regions, that's going to be an sp3 hybridized atom. Gosh, this is messy. sp3. And an example of this would be methane. right? Now, methane is an example of a tetrahedral molecule. And the hydrogen-carbon-hydrogen bond angle is going to be 109.5 degrees. Now, it's very misleading because this looks like it's a 90-degree angle. It is not a 90-degree angle. The three-dimensional model of this is something like this, where this hydrogen is coming out of the page towards you. Like imagine something jumping out of the screen towards you. This hydrogen is going into the screen. Imagine something shooting into your computer screen, like going away from your face. So they're not in the plane of your screen. Whereas these two hydrogens, they are exactly on the plane of your computer screen, right? So it's not a flat molecule. It looks like a little pyramid down here with a little guy sticking up on the top. Okay, and the angle is 109.5. The next example would be one lone pair and three bonding regions. Still sp3, right? An example of this would be ammonia. This is an example of trigonal pyramidal, trigonal pyramidal. Okay, now it looks too like all of these things are on the plane. In reality, ammonia has one hydrogen that is coming out of the plane and one hydrogen that's going into the plane. So this hydrogen in yellow is like going past your computer screen away from your head. This hydrogen here is coming out of the computer screen towards your eyes, right? So they're not on the same plane of your computer screen. This hydrogen here, though, is on the computer screen. So the bond angles that we need to focus on here, so a hydrogen, nitrogen, hydrogen bond angle, these are going to be 107 degrees. Okay? 2.5 degrees less than the tetrahedral. Yeah, we'll go with that. That's fine. Okay. The next one is two lone pairs, two bonding regions, still sp3 hybridized. The example here, water. Both of these hydrogens are in the plane of the screen, so they're like, it's all laying flat on your computer screen. This is what we would call bent molecular geometry, and the hydrogen-oxygen-hydrogen bond angle is 104.5 degrees. So basically, for these three, and you do have to memorize these bond angles, it is critical. And I know that they don't match what's up here, but that's okay. These in orange are what you do need to memorize. What you can think of is start with 109.5. Each lone pair that you add takes off 2.5 degrees. So this one lone pair here takes off 2.5 degrees from the 109.5. And then you add on this extra lone pair, a second one, and you take off another 2.5 degrees. So you go 109.5 to 107 to 104.5. However you want to memorize that is up to you, but each lone pair essentially decreases this bond angle by 2.5 degrees. Okay. The next type of molecular geometry we're going to be dealing with is, oh gosh, two lone pairs, three bonds. Is that true? Oh, I erased stuff. Let's erase these as well. Boop, boop. Okay. So the next one we're going to be dealing with are ones that are most often tested. So you have 0 lone pairs, 5 bonds. This now we're in sp3 hybridized. An example of this would be PCl5. And I'm not going to put the lone pairs on the chlorines because it's just going to waste time. Okay, the molecular geometry for this one is trigonal bipyramidal. And there are two bond angles you need to understand. So let's draw this out. We have P, Cl, Cl, Cl. And then we have a Cl up here and a Cl down here. So you get the trigonal bipyramidal because you have basically a triangle here that forms one pyramid on top, and then you have a second pyramid that forms on the bottom, right? So you have pyramid number 1 up top and pyramid number 2 on the bottom. That's the bipyramidal part, all right? These, let's erase some of this stuff. The chlorines here, this guy, and this guy, imagine they are all on the same plane. So we're going to draw like a little triangle between them. Okay? The bond angle for these chlorines and phosphoruses, so like this chlorine, phosphorus, chlorine bond angle here is going to be 120 degrees, just like the trigonal planar. So if we were looking down on this molecule from the top, so I'm going to draw like a little eye up here, right? If we're looking down on it from the top, bird's eye view, okay, what you would see is you would see a chlorine. There's a phosphorus underneath that chlorine, and then you've got a chlorine out here, here, and here, right? Remember, underneath this chlorine here in the middle, you've got like a little phosphorus, this phosphorus here. Now, what shape do these chlorines take? They take the same shape as trigonal planar. And the angle we know for trigonal planar is 120. So one of the angles for trigonal bipyramidal is 120. Okay, it's between those. This is bird's eye view. Bird's eye view. The angle between those chlorines and phosphorus is 120. Now, there's a second angle here, which I'm going to draw over here to the side. So we've got phosphorus, the chlorines. If we look at this chlorine and like this chlorine, we're really interested in this angle here. So now we've got chlorine, phosphorus, chlorine, but this is for the chlorines in green. This angle is going to be 90 degrees, right? Because basically if you look at this from the side, what it's going to look like is, and then you've got other things going on. So that's going to be a 90-degree angle. So your two angles for trigonal bipyramidal are 90 degrees and 120 degrees. 90 and 120. Okay, that's probably the hardest one, but one of the most tested structures as well. So let's say we have one lone pair and 4 bonds. This is still sp3d, and an example of this would be SF4. So we have S, F, 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 F. Again, the lone pairs on the F's. I'll draw it this time because I'm feeling like doing that. And then we've got a lone pair here. So this would be called seesaw. And the reason we call it seesaw is literally because it looks like a seesaw. So we've got the sulfur, a fluorine, a fluorine, fluorine, fluorine. So this fluorine is coming out of the screen. It's coming towards your eyes. This other fluorine is going into the computer screen away from your eyes. And so literally it's as if you have a little person here and a little person here, and they get to ride back and forth on the seesaw, right? If this is the ground then this fluorine can go up and down, that fluorine can go up and down, right? It literally looks like a seesaw. Okay, so that's why we call that seesaw. Let's see, I'm trying to erase all this stuff. Okay. So the bond angle between this fluorine and this fluorine, so we've got fluorine, sulfur, fluorine, it's these guys. It could also be between like the top fluorine and this fluorine. It doesn't really matter. Is still going to be 90 degrees for the same reason as this one is 90 degrees. But then this fluorine and this fluorine, they're going to have a bond angle that is less than 120 degrees. Now, the reason for that is because normally you would think it would be 120 degrees like in PCl5. However, this lone pair takes up a lot of space, right? Lone pairs like to take up a lot of space. And so we know based on Coulomb's law that electrons repel each other. These lone pair electrons repel against these bonds and force them closer together. So it's basically pushing that fluorine and that fluorine closer. So lone pairs push fluorines closer together, right? And so that's why it's less than 120. We're not really interested in why it's less than 120. It just is. Okay. The next example would be 2 lone pairs, 3 bonds. This is still sp3d. An example of this would be ClF3. I'm going to put the lone pairs on it this time. And now I've got 2 lone pairs on the central atom. This is called T-shaped. And it's because it literally looks like a T, right? That's where the T comes from. So it's T-shaped. This angle is 90 degrees. The next one, we would have 3 lone pairs, 2 bonds. An example of this is XeF2. So we've got xenon, fluorine, fluorine. We've got 3 lone pairs around the central atom, and this would be called, this would be linear, another linear, because it's a straight line, right? We're not interested in the lone pairs, we're just interested in the bonds. Now, I've got to add on a separate page, new page. Woohoo! I don't want to copy some stuff, so we're going to copy all of this. Boop. Nice. Heck yeah. Here we go. All right. So we have 0 lone pairs, 6 bonds, sp3d2. An example of this is SF6. And the bond angles in between all of these is 90 degrees. This is an example of an octahedral molecule. The next example is 1 lone pair, 5 bonds, still sp3d2. An example of this would be BRF5. One lone pair down here. So this is what we would call square pyramidal. And the reason for that is because if you look at this molecule, what's actually happening is that at the base, we've got a square, and it forms a pyramid. It literally forms a pyramid. So bromine and those 4 fluorines form the base of the pyramid, and this fluorine at the top is the pinnacle, the top of the pyramid. And it's literally, it looks like a square pyramid, like in Egypt, those pyramids. And so the bond angles for everything here is still 90 degrees. And you've got that lone pair chilling on the bottom. The final geometry we have to deal with is 2 lone pairs, 4 bonds, still sp3d2. An example of that is XeF4. Lone pair here, lone pair here. Obviously, there are lone pairs on all the fluorines. This is what we would call square planar. And the reason for that is maybe you're putting it together. It actually forms just a flat square. So like a piece of paper. It all just lays flat together. So I explained all these things, and hopefully now you can go back and, you can look at this table and start to piece these things together. For example, that last one we talked about, 2 lone pairs, 4 bonds, 6 total regions, which means that it's sp3d2. 1 plus 3 plus 2 is 6. So all of these are sp3d2. All of these are sp3d. These are all sp3, sp2, and sp hybridized. Right here are all the names. The angles that are most important are linear, trigonal planar, tetrahedral, and I gave you the angles for these. So this is 107 and 104.5. We have the angles for trigonal bipyramidal. We have obviously linear again, octahedral, and then these. These are really the only angles that matter. Right, this chart gives just a lot more information than is necessary, but these angles in green are the ones that really matter. Okay, so hopefully that kind of helps us get started on our journey with molecular geometries. Really, all you need to do is just figure out how many lone pairs and how many regions, and then apply that to whatever like geometry it is.